Okay. All right, so you guys have these notes in front of you, and if you don't, you're looking up here and just kind of refreshing your brain. Okay, so hopefully with the project that you guys started on Friday, you started reminding yourself of those big differences between your covalent and ionic compounds. Yes? Kind of ish? A little bit? At least a little bit. Hopefully you kind of remembered a couple things about ionic. So a couple of the main things that we want to focus in on, we're going to come back to metallic later, but that one is between your metal and a metal. Okay? Excuse me. Your ionic is between a metal and a nonmetal, which means you have a cation and an anion. Which one is the one that gives away an electron? Cation, great. Okay, so so the whole idea is that cation is going to give away its electron, and the anion is going to accept it. So one becomes positive, the other one becomes negative, and then they stick together. So is it just two things? Looking at my little lattice that I'm holding up, is it just two things? No, it's a whole bunch of things that are positive and negative that are all just kind of sticking together. All right. So ionic compounds. That's why I usually try to stay away from ionic bonds, because a bond sounds like it's between a couple things. An ionic compound is like a whole mess of what do we call this, by the way? You guys had this in your project. Starts with this crystal lattice. Exactly. All right. And so it's a bunch of positives and negatives held together. What is that force that holds them together? What happens if you go across the carpet like this? And static electricity, right? So it's electrostatic forces. That's what static electricity is. It's still that connection between a positive and a negative thing. That's why you zap your finger. Same thing with this. It's an attraction between positive and negative things. They're held together. Super, super strong forces here, okay? It's really hard to break electrostatic forces, okay? Cool? All right, so next. Then you guys had this whole business where you had to draw this. And you will have time today to practice this. We'll be doing a bunch of drawing, but I'm going to mix it up. We're going to have covalent and ionic today. So right here, as you guys can see, I feel like I should be standing in the back. I'm going to stand in the back. All right, so now I'm out of your way. All right, so as you can see here, what you start with is you have your little electron dot notation. Where do we get this information from? The periodic table, good. So more important or more specific is their groups, correct? So when we look at their groups, what does group 1 have? How many valence electrons does group 1 have over here? Oh, sorry, I missed the 1. All right, but how many? They have 1. And then how many does the group 2 have? 2. We're going to try this again. Here you go. There you go. All right. So you can kind of look at their group numbers. So what does 15 have? 5, good. So we got that right there. We did. You can look at the little a, or you can look at 15 minus 10. What about these guys in the middle?
1 or 2.
What?
1 or 2.
No. You don't know. Okay? You don't know. They all have different ones, okay? So those we tend to have to figure out. Okay. So now that we've got that reminder, basically when we're looking at these little drawings, okay, you have your electron dot structure for both your cation and your anion. We have to show the transfer with an arrow, and then you have to write them in brackets. Brackets is the one thing that you always forget, okay? And on our benchmark specifically, you guys got to see them get filled in with little dots on the chlorine. Did you guys see that? Your anion had a bunch of dots. Does anybody remember that? Yeah? Those don't look like dots, I know, but just like imagine them. There's 8 of them. All right, so what you're showing there is that electron actually got transferred and there are 8, okay? And the other one doesn't have any, so he gets a positive one, the other one gets a negative one. And down here, for the one that has 2 chlorines, because we needed 2 to fill up, to have calcium give away both of its electrons, those guys are also going to be filled up, so they're going to have 8 around it, and I'm not even going to attempt it. Okay, so does anybody have any questions over drawing these? So I'm requiring you to be able to do those 3 steps. Does anybody need a refresher on anything? Okay, so moving on, turn the page. All right, so the next little step with our ionic compounds was we took our little symbols, we gave them all charges, and then we crisscrossed them. So it's the crisscross method, all right? And this is the one that once I teach you prefixes, everybody forgets this for some reason. So this is why I'm reminding you, this still exists. If you have a metal with a nonmetal, you figure out what their charge is, and then you You write them above, you crisscross them, and those become the subscripts. How is it different for covalent? Somebody tell me how it's different for covalent. Where do you get your subscripts from for covalent molecules or molecular? Starts with a P, you guys. You did a whole Pogel on them. Mono, di, tri, tetra, penta. All right, the prefixes. All right, so the prefixes are what give us those numbers. So it's different, all right? So when I give you the name of a compound, you get it from specifically what the prefix is, all right? You have to know a little bit more about a compound. I can't just randomly say, hey, mix these two together and see what you get. No. This one, we can do that. We say, what is it if you mix an aluminum with a bromine? And then you have your charges and you have to crisscross them, okay? So, so let's review those charges real fast. Okay, what do we have for the group 1? What's their charge going to be? Positive. Okay, remember, your charges come from how far away they are from being a noble gas. So remember, your periodic table kind of gets folded into a column. So how far away is this first column? They have 1 extra, right? So it's +1. All right, column 2 has what? +2. How about these guys? We don't know. They have different ones. We got to figure them out. How about boron family? +3. Carbon, now you can go. Plus or minus 4, and then we start our minuses, and we have -3, -2, -1, all right? And remember, these guys are the ones that kind of give you your information for your transition metals, and that was the stock system that I'll review in just a few, okay? All right, so, so when we're looking at this, let's go to the calcium and oxygen example. What was calcium's charge? I'm sorry, it's easier for me to write if it's zoomed in, so I'm going to zoom in. Just stay with me. All right, so what's calcium's charge? He has a +2, good. What's oxygen's? -2, so then we crisscross E like so, and we end up with Ca2O2, correct? No. What does it have to be? CaO. Okay, so the reason why, when you're dealing with your ionic compounds, we do need them in the simplest ratio, because this is what I want you to picture. This is why. Because we wouldn't say, oh, well, we need 2 calciums and 2 oxygens specifically, right? That doesn't make sense. You just want to know what is the simplest ratio to shove them all together, all right? So think about the lattice. That's what it comes down to. It's just a bunch of electrostatic forces, okay? All right, so, and then you also have these guys. That's one of our examples of a transition metal. That's the stock system. We would call that chromium 4 with a Roman numeral 4 oxide. And that tells you that it had a +4 charge. Okay? All right. Next, we've got polyatomic ions. So if you are looking to be in AP chemistry, you are supposed to start memorizing these, right? Does anybody remember the sentence-ish? Anybody? Something about a Nick the baby camel ate crates of inch clams for supper and Phoenix. Good. All right, so all those represent the 8s. So once again, if you're trying to memorize those, at least get your 8s down, and then I can teach you the rest. So, but otherwise, where can you find all of your polyatomic ions? In the periodic table. Everybody open up your periodic table, take a look at them, remember them, look at them, recognize them. They all have a certain number of oxygens, and they all have, what else? What do they have to have if they're in an ionic compound? They have to have a charge, don't they? What kind of charge do all of them have except for ammonium? A negative something, right? Okay, so remember that these guys count as your anion, and you still are crisscrossing, just like we did down here. Okay, you're still crisscrossing. What I recommend is, until you become really, really good at polyatomic ions, always put them in parentheses. Just put them in parentheses so you know they're a thing, and then you crisscross them and you know to put it on the outside. Okay? Okay, so next we had how to write their names. It's been pretty simple. Remember, you go metal something ide. Do we have any prefixes? No prefixes for ionics, you guys. Okay, it's just metal something ide. The charges take care of how many of everything we have. Okay? Any questions on this? We're all okay? Okay. Okay. All right, let me push that out of the way. Go ahead and take a look at your stock system notes. And can I actually take a picture of somebody's real quick? Unless I have it. Nope, I don't. Of whose? Oh, okay.
Well, mine doesn't look really pretty.
It's beautiful. The only thing is it has pink. I don't know if it'll show up. This might be okay. Just a second. I just need a light. I hope this isn't recording me like this whole time because I can't cut it out. It doesn't let me like delete things on this thing. Oh, it's recording. Hi. Okay, sorry. My bad. All right. So so you guys took notes. See? Did you guys see how the screen changed?
Oh, yeah.
Yeah, why does it do that? It's really frustrating. All right, so so these notes we also took, and so just a reminder, the stock system is because we have those transition elements, everything below metalloids line as well, so they aren't in that middle section, but they still count as well. They have different charges, so we have to be really specific about who we're talking about. Copper 1, copper 2, lead 2, lead 4, tin 2, tin 5. There's all sorts of different flavors out there, okay? So what you do is you're going to be paying attention to your anion, all right? This is the most important guy when you're dealing with these, all right? So you guys took notes over kind of how to solve for it, all right? And so what you're doing, I gave you guys the example of chromium. Should have been 3, I think. We'll look at it. Okay, we'll resolve it real quick. All right, so what we have is sulfur had a -2 charge. How many sulfurs did we have? 3. So that came up with a whole side of a -6. If these are neutral compounds, okay, if they're neutral, that means they have a thing equal to 0. What does positive have to be equal to? If this is a -6, this has to be a +6, okay? But then we have to focus in on how many we have. Since we have 2, what can we split 6 into? 3 and 3, right? So this is actually chromium. Oh, I see it now. I thought you had it in a box. I'm sorry. That's why I was like, why does she have that? All right, so make sure you put your parentheses. That'll help. Okay, so put parentheses around it if you don't have parentheses. That helps us know what we're dealing with. All right, so we have chromium 3 sulfide. Once again, these kind of give you issues because this is supposed to be copper 2 oxide, but we don't have any subscript to kind of tell you that. So just make sure you run through. The anion will always give you the information you need about the cation that you're looking for, okay? And then when you go to write it, just make sure you're still simplifying things down and use your Roman numerals. Any questions on stock system? Yes. Up here? So transition, sodium, copper 1. Okay. Okay, cool. So now turn in your packet to the covalent part. All right, so we also did covalence, all right? And for your covalent or molecular compounds, just remember that this is between a nonmetal and a nonmetal. You had a whole stinking long pogo on this about the naming, and they use what? We just asked you 5 minutes ago. Prefixes, good. All right, so let's run through all the prefixes real quick. So what's 1? Mono, 2? Di. 3? Tri. 4? Tetra. 5? Penta. 6? 7? 8? 9? Nona. Usually it's Nona. Okay, Nona, N-O-N-A. And then what's 10? Deca. Good. All right. Okay, so you got all those prefixes. Do we ever put mono on the first one? No. Never. All right, but otherwise it's fair game. You put whatever you need to put on those guys. And it comes from those subscripts, okay? So the next thing was on Friday you were supposed to watch the video for NAS. How many of you guys honestly watched it? Yeah. Okay, so if you didn't, I'm just running through it very fast right now. And that is not going to teach you it. You need to watch the little video. It's 5 minutes. It doesn't take away from your life. Watch it while you're waiting in line for lunch. Okay? So so we're gonna use NAS to go over carbon dioxide. Up here on the board, I do have what the different letters stand for. So N is going to be needed. For the most part, on your periodic table, everybody needs 8. There are 3 exceptions. You don't have to worry too much about them except for hydrogen and helium, I think pre-AP year. Okay, so helium. How many does hydrogen and helium need?
1.
They only need, not 1, 2. I can't live right now. Oh my gosh. It won't stop. How do I get out of it? Okay, so hydrogen and helium, they're part of the 1s2 orbital. You guys remember when we did electron configuration? So how many do they need? 2. That's all that'll fit in their shell, and that's what you got to think of, all right? It all comes back to electron configuration. So hydrogen and helium will only need 2. The other 2 exceptions that you don't have to know about so much right now is going to be beryllium and boron. They need 4 and 6, okay? They're just random. Don't worry about them too much. I'm not going to have you guys draw them, okay? But if you happen to see an example of it, I just didn't want you to be like, well, they don't have 8. That's why. They're weirdos. Okay? I know. I'm so mean to them. All right. So let's go ahead and start with carbon dioxide, all right? Using this NAS method, we have the needed minus available, meaning how many valence electrons do they have. And then the S stands for how many they're going to share. How many things get shared in one bond? How many electrons? 2.
Oh, yeah, 2, that's right.
2 electrons get shared, all right? So 1 and 1, and they hold hands, okay? So that's why we're going to divide by 2, and then you have your bonds. So for carbon dioxide, let's go ahead and write NAS on the side. I want you guys to do this with me. Okay, go ahead and put a subtraction by the A and an equal sign right there so that you know what you're doing. Okay, and people who don't have this, you should be writing this on a piece of paper. This one's an easy one to write. Okay. She doesn't want to. Okay, so for NAS, we're going to go ahead and run through how many we need. Carbon. How many does carbon need? Don't worry about this whole part, by the way. Just look at the formula. How many carbon need? Carbon does not need 4. What does he need? How many does everybody need?
8.
Thank you. All right, so we've got 8 for carbon. We have 2 oxygens. So how many does each of those oxygens need? It's not a trick question. How many do they need? Thank you. 8 plus 8. All right, what is 8 times 3, everyone?
24.
Good. So we're going to put a 24 right here. Okay. Now we're going to look at available, which is the one that you guys wanted to answer just a second ago. How many does carbon have available? Wrong. 4. Okay. How many does oxygen have available? 6. How many does the other oxygen have available? 6. All right, what is 6 plus 6 plus 4? 16. All right, what is 24 minus 16?
Oh, wow.
What is it? 8. Thank you. All right, so we have 8 things that need to be shared. So in order to figure out how many bonds, we divide that 8 by 2. You're fine. All right, so 8 divided by 2 equals? Good. All right, so we're going to have 4 bonds. All right, but that's not where you finish. You got to draw it out. All right, so what we're going to do is I'm going to move mine down so I have a little bit more room off to the side. There we go. All right, so you're going to throw, carbon likes to be in the middle. You guys heard that on one of the videos, and I'll show you guys a video tomorrow that's kind of funny about it. But carbon goes in the middle. Whenever he has the chance, throw carbon in the middle. He's in the middle. Okay? All right, so carbon's there. There are 4 bonds for carbon. However, how many oxygens is he linked up with? There's only two. So if you notice that it's not going to be four things it's linked up with, maybe put your letters first. So we're going to put our two oxygens there. And I have to have 4 bonds coming from that carbon. So what we're going to do is we're going to go 1, 1.
Oh, I remember this.
And now we have to go, oh, they're double bonded. Double bonds are a lot stronger than single bonds, and triple or even more. Good job. All right, but we're not done. We're still not done. All right, so what you do, once you've drawn this much, we've gotten our bonds out there, we go back to that available number. What's our available? Right here, I just circled it. 16. Okay, so these bonds each account for how many electrons? 2. So we have 1, 2, 2, 4, 6, 8. We need 8 more. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8. Until everybody kind of gets filled up. Okay? So that's NAS method very quickly. If you need it slower, go watch the 5-minute video, please. Okay? All right. So we're going to do one more example together. Squeeze over to NH3. Okay? All right, let's start with NAS. Okay? I'm going to pause this. I'm going to have you guys work through it, and then we'll check our answer. Okay, so we found that we had 14 needed, 8 available, and that meant we had 6 things that are going to get shared, so it's going to turn into 3 bonds. So we put nitrogen in the middle because he's sort of close to carbon. Carbon likes to be in the middle. And then we put the 3 bonds connected to it, and we connected all our H's. All our H's are satisfied. They all have 8. I mean, not 8, but they're full. They have 2. Okay? So we still have to match up to this. Each bond accounts for only 2 electrons, so we have 2, 4, 6. We need 2 more, so we're going to put a lone pair on our nitrogen. Now, this is not really showing what this guy looks like too much. Sometimes we like to put our bonds at angles because this one is actually standing up kind of like this. Kind of looks like this, just so you know. And then the lone pair sits on top. So if you notice, a lone pair is always going to push bonds away from it. You guys kind of see how, can you imagine that? A little lone pair sitting on top of it?
Why did you put 2?
And it pushes it away.
Like, why did you put 2 on the top if they both count for 2? I don't know. Like, does 1 dot count for 2?
No. Line. One line counts for 2.
Oh, okay.
Okay. All right. Cool. So what we're going to do now is we're going to go to our